Welcome our student to the stream processing in biotechnology. We continue the lecture on adsorption. As I previously we talked about the batch adsorption. Now we will consider the continuous stirred tank adsorption equipment. Mostly we use the continuous stirred tank for a large scale production. It can be effectively used for whole beer processing. For this case, the tank initially contained pure solvent. The operation of the continuous stirred tank is tank initially hold like the pure solvent and unloaded adsorbent. For this case, it's only the solvent and sorbent with no solute adsorbed on the surface. That's right. The flow steadily out of the tank, but its concentration varies with time. That's right. We have the flow, and then we feed solute solution to adsorption unit. We feed in, feed out continuously, but concentration is unsteady state. The flow is steady state, but concentration is unsteady state. Because concentration is dropped with time. Why? Because the amount of solute is adsorbed on the surface of solid. That means C is the concentration that remains in a solution. That means it's dropped with time. C is the function of time for this case. And also for this graph show you the performance. That's right. The concentration or exit concentration of the adsorption unit with respect to. For this case, if the concentration is rapidly increased, that means there is no adsorption or low efficiency adsorption because the concentration is increased. That means solute in and solute output will approach the same. There is no adsorption. And the rapid adsorption for that case, the concentration is initially increased, and then it's constant for a period of time until it's rapid increase. That's right. What does it mean? If the adsorption shown after that, the rapid increase of concentration means there is no adsorption for this. Why is no adsorption for this? Because adsorption is in equilibrium with the solute already. If it is equilibrium, the adsorbent cannot use for fat. How to prove it? You have to regenerate adsorbent and then adsorption again. And the typical adsorption like this. That's right. Like this. And if you make like the mass balance of solute around the continuous tank, look like this. That's right. It look like this. This includes like the input, output equal to accumulation. Please remember that concentration of solute at the exit is depend with time. That's right. Depend with time for this case. Okay. We have at least 3 terms. The first term, this term, the change or accumulation of solute in the void. That's right, in the void. There are some void. We have it the adsorption in the adsorbent with porous material. That's right. There are some solute between the porous material or between the void in the solid tank. That's right. The void is maybe void inside the pore and void between the adsorbent outside the pore. It's outside the surface of adsorbent. That's right. For this case, it's in the void. That's right. In the void between the adsorbent. And for this case, amount of solute adsorb on the surface of adsorbent. That's right. This is and the surface of adsorbent is in the void between absorbent and adsorbent in the side of the pore also. And this term is flow in, flow out. That's right. FCF is amount of solute in the flow in. FC is amount of solute in the flow out. That's right. V is the volume of the tank. That's right. CF you know already. F is amount of feed. Q is amount of adsorbent. That's right. Okay. Similar mass balance on the adsorbent. If we balance at mass balance on the adsorbent, this is amount of solute adsorbed on the adsorbent equal to VR. V is the volume of tank. R is the rate of adsorption per volume of tank. That's right. For this case, we have 2 limiting mechanisms are common for controlling the rate of adsorption. It depends on diffusion from the solution to the adsorbent Or the second step is diffusion and reaction within the adsorbent. Mostly we have the diffusion from the bulk solution out of the adsorbent, that's right, diffuse to adsorbent. And the second step, the diffusion in the pore and reaction step in the surface. It may be no reaction, it may be integration, it may be ionic change, it may be affinity. We call in this reaction or interaction in the surface. We have two, that's right, diffusion control and diffusion and reaction control. Right. This show you the most diffusion, that's right. For the bulk liquid or gas, the solid adsorbent, that's right. And also we have the flow of solid in liquid or in gas. There are some film of liquid or film of gas. It is film, that's right. And also the solute diffuse from the outside the film, that's right, diffusion, and then diffusion across the film, number 2. Number 3 is diffuse or flow inside the pore, that's right, flow inside the pore. Number 4 is attached in the surface. Or reaction number 5 is maybe integration. It may be moved to the side that is proper side, something like this. This is the step for adsorption. The step for adsorption. Right, okay, then we back to talk about the rate of adsorption. For diffusion in the solution control, for diffusion control, the rate of adsorption is expressed in this term. R equal to KAC minus C star. C is the concentration of solute in the solution. C star is concentration at equilibrium. That's right. K is mass transfer coefficient. A is the surface area of adsorbent per the tank volume. That's right, per the tank volume. Okay, for example, because this is in equilibrium, for example, you can just find the Frederick, that's right, Q equal to K C star power n, something like this. The adsorption kinetic of this case a function of Stirling application speed, but not strong function of temperature. Only the adsorption kinetic depend on the rest or the Stirling or speed of the impeller. Something like this. It's not strong function of temperature. Okay, if for the diffusion and reaction control, the rate of adsorption may be expressed in this term. It also depends on diffusivity. Diffusivity. K is rate of reaction constant. If K is first order irreversible reaction, is approximately for our assumption. For this case, in principle, we can now solve for exit concentration and the adsorbent loading Q. We do by the combining the integration of mass balance of this equation, and this equation we have these two, but this two is a function of rate of adsorption. You have to combine with diffusion control or diffusion reaction control. That's right. But this equation is nonlinear. As nonlinear, it's difficult to solve by analytical technique. We can solve this equation by the numerical method. If you look at it, is for this case is ODE. This is the ODE, but it's two equations. That's right. Two equation, but nonlinear equation. It's difficult to solve by analytical. But numerical technique is better. That's right, to solve for this equation. Okay. On this, for initial estimate, too easy, we can estimate. We can assume the adsorption is linear. If we assume the adsorption is linear, we can integration these two. That's two equation. That's right. That's two equation. We can integration, and then we get the result at this. That's right. This for approximate solution. With Q is a linear function of equilibrium concentration. We get this expression. We get the expression. It's our solution. And also, what is sigma? Sigma is expressed in this term. Expressed in this term. The sigma is positive and negative side. Positive and negative side of sigma 1 and sigma 2. This is sigma 1 and sigma 2. Sigma 1 and sigma 2. You can calculate from. This is the sigma 1 and sigma 2. Okay. Okay. When you use this equation, I will talk about more this equation, how to use this by the Next example. For this example, the whole beer containing antibiotic novobiosin. That's right. What contact with an ionic chain resin substance in acrylic tank. For this case, we use a continuous acrylic tank. The resin is ionic chain resin. That's right. To absorb antibiotic. That's right. From the beer. That's right. Okay, the tank initially held 0.876 liters of liquid. In the tank, initially we have 0.876 liquid. This liquid, no antibiotic. That's right. This no antibiotic is a pure solvent. And also the tank also held 0.25 liter of resin, which initially contained 1.35 gram per liter of antibiotic. What does it mean? That means initially we have pure solvent and we have resin, but resin is attached with the antibiotic 1.35 gram per liter. Okay. For this case, the whole beer containing 640 microgram antibiotic per cubic centimeter fall into the tank with the feed of whole beer. The feed beer is 640 microgram antibiotic per cubic centimeter. That's right, flow into the tank continuously. That's right, the less of the flow, the less of the beer. That's right, the flow rate is 2.7 liters per hour. And also the outlet concentration C was measured by UV spectrophotometry. It's the result of concentration at the exit. It vary with time. That's right, it's vary with time. The temperature was constant at 35 degrees Celsius. The pH it remained in the range of 6.8 to 7.2. The question is calculate the resin loading Q. Q is a function of T. Then estimate the rate of constant Ka. That's right. Predict from the simplified theory. From the data, you have to calculate loading Q is a function of T and estimate the Ka. Ka is mass transfer coefficient multiplied by surface area of solvent divided by volume of the tank. Volume of the tank. Okay, the first step, back to the equation, right? dq by dt. Back to the first equation for the absorption. This equation, that's right. And then the rearrange this equation and then integrate this equation. We rearrange this equation and then you can move dq and dt separately. For that case, you can cancel. That's right. dq equal to dt. That's right. You modify dt. Okay. This term is dt. That's right. This term is dc by dt is with respect to dc. That's right. FCF dt. That's right. FC dt. For this case, dc by dt multiplied dt with cancel is dc. Okay. For this case, you integrate three terms. That's right. This term is separate into. That's right. And this term is this. Okay. For this case, you integrate dq from the maximum to the q at any time. And dt, you have to integrate from 0 to t. That's right. FCF divided by 1 minus epsilon v dt minus c fc divided by 1 minus epsilon v dt integrate from 0 to t. And the last term for this term. That's right. Okay. You know f is constant, c is constant, 1 minus epsilon constant, v is constant. You can integrate dt, you get t. That's right. From 0 to t, you get t. Integrate q, you get q. That's right. Q minus q, q equal to q0. Okay, this term. This is constant. This constant. That's right. This constant. That's right. This also constant. Okay. Integrate dt, you get t. From 0 to t, you get t. That's right. And the second term, f divided by 1 minus epsilon v. This is constant. Integrate 0 to t c dt. C is not constant. C is a function of time. Okay. The last term, epsilon divided by 1 minus epsilon is constant. Okay. Integrate c DC, you get, indicate DC, you get C. From 0 to C, you get C. That's right. It's only one term that it is in integration. You have to find C. You can integrate this by numerical, or you can integrate this by the fitting in this equation with time, and then you can integrate analytically. For this technique, I will integrate this by analytically. Okay. The first step, we have to substitute all known value. You know Q0, that's right. You know F, you know CF, you know epsilon, you know V. You substitute this in the equation. Okay. This is Q0. That's right. This is F. This is F. That's right. What about the epsilon? This is F. That's right. What about the epsilon? Epsilon is 0.8676. That's right. This is the initial tank held 0.86 liters of liquid. That's right. And which contain no antibiotic. The tank also held 0.25 liters of resin, which initially contain 1.35 grams per liter. That's right. This is the amount of liquid. That's right. We know this amount of liquid. This is the Y. That's right. This is Y is equal to amount of liquid. That's right. And also amount of solid. This is amount of solid. Mean 1 minus epsilon. This is a solid volume. This is a white volume. That's right. The initial liquid indicate the white volume. Initial solid indicate the solid volume. That's right. Okay. For this case, epsilon is 0.876. That's right, 876. And 1 minus epsilon is equal to the volume of solid is 0.25. Okay, you know F, you know CF, you know V, you know epsilon, and 1 minus epsilon. Yes. To substitute all of this, you need only C and T. That's right, C and T. You know C already with respect with time. You substitute C, you can calculate Q is a function of time, but this is in terms of integration. What does it mean? You can integrate by numerical, but for this technique, I will integrate by the substitute the fitting equation of C. Right. How to do this? We plot C from this data with time. We plot C with time, and then you fitting the equation. Is it? You fitting with this equation. This is C. That's right. You get C is a function of time. You substitute C into this equation, and then you integrate. That's right. And then you integrate. Okay. From this case, you substitute C and integrate. You substitute C. That's right. You get Q is a function of time. Okay. Q is a function of time. You substitute. 5 เพิ่มอยู่กับที่ time 0.5 and then substitute C is 138. That's right. 0.5. C is 138. You substitute this and integration, and then substitute T. You calculate Q. That's right. And then you can calculate Q like this. At time 0.5, C is 138, and the integration from 0 to C. That's right. You get this term, and then you substitute into the equation this. You get Q as a function of time. That's right. You get Q as a function of time. This is our question. It's answered already the first question. That's right. And also you can show in the graph Q and time. Time increase, Q increase. For the next step, how to evaluate Ka. How to evaluate Ka? You can plot log CF minus C versus time. That's right, from this equation. This. You can plot log C versus time. And then you can calculate sigma 2, and then you can evaluate Ka. In this case, after you plot, you have some drop rapidly at the initial time, but also then it's follow the trend is the linear relationship. That's right. To find small value Ka, we plot this. That's right. The data drop at the small time, but then linear at the larger time. Okay. From this case, you can calculate sigma at the slope. Slope is sigma 2. Slope of this curve is sigma 2. That's right. It's about 0.13. That's right, per hour. That's right, per hour. It's minus value at sigma 2 equal to 0.1283 or approximately 0.1 t. For this case, at the last time, also we can estimate the equilibrium constant K. At the larger time, we can estimate the equilibrium constant K is equal to C divided by Q. Right? From the data, you can estimate K. You can estimate K. This is C. 401 S, 418, and also Q. Q is 25 or 2T. Okay, K is estimated from Q divided by C. This is the conversion unit. Convert the unit from microgram to milligram to microgram. And then you get K equal to 60.36. 60.36, that's right, for this case. And then you can evaluate Ka in terms of this, in terms of this equation. You know sigma 2 is up to F, epsilon V, epsilon K, that's right, you know F, epsilon V, epsilon K. You substitute all this and then you solve for Ka. It's a nonlinear, that's right, you can solve for Ka. After solving, the result is 9.27. That's right. 9.27. Please remember that if Ka is increased, rate of assumption is increased based on the rate of assumption equation. That's right. I equal to KAC minus C. That's right. K is the mass transfer coefficient. A is the surface area of the absorbent per volume of the tank. I will stop the lecture for this, and then I will continue for the adsorption in the last section. For the fixed bed adsorption is the most common use for this. Okay, I will stop for the lecture. That's right.